Okay, so this is my comprehensive guide on naming compounds. This will take you through all of the ionic, all of the covalent compounds that you're looking for. We'll go over how to name them. We'll go over how to write some formulas for them. Let's get started. So make sure you have your periodic table with you. Make sure you have your polyatomic ions list. The main ones I'm going to be using are these bold ones. And for my chemistry students, you want to make sure you have those memorized. Physical science, I said you can use this list. So let's begin. So the first thing you always want to determine when you're looking at a formula. So we'll start with naming. Step 1, determine ionic or covalent. That's always going to be your first step because you name them differently. So how do we actually do this? Well, ionic is always going to be made of a metal plus a nonmetal. Or if you see any polyatomic ion, you know that you're dealing with an ionic compound. So if you see any of these, that tells you right away you're dealing with an ionic compound. Covalent compound is always going to be a nonmetal and a nonmetal. So let's make sure we're clear on how we actually identify metals and nonmetals on the periodic table. I'll kind of show my periodic table here. Now, in general, your metals are going to be all of these, with one exception, hydrogen. That's a nonmetal. Your nonmetals are going to be all of these, plus hydrogen. So let me just real quickly fill this in. Fill this in. Two metals. Alright, so that's a real brief sketch here. We can see that the metals are all of these, plus hydrogen up here is a nonmetal. These are your nonmetals up here. And if you ever see anything down here, that's going to be a metal too, but we're not really going to deal with these on the high school level. Maybe when you get to your doctorate in chemistry. Anyway, step 1, determine if it's ionic or covalent. So let's run through a couple quick examples. If I give you NaCl, you're going to look at your periodic table. You're going to find these elements. Na, metal. Cl, nonmetal. Metal plus nonmetal. Ionic. So you see something like CCl4. Copper, nonmetal. Chlorine, nonmetal. Nonmetal plus nonmetal, covalent. If you see something like AlPO4, as soon as you recognize this as phosphate on your polyatomic ions list, we know that this is going to be ionic. So any polyatomic ion equals ionic. So, once again, step 1, determine ionic or covalent. Once we've found that, we go 2 different ways. So, if it's covalent, I'm going to start with this because it's simpler. We name it using Greek prefixes. So, however many atoms you have in the compound, that's the Greek prefix you need to use. So we're going to run through these quickly. You have to memorize these. So 3, 4, 5, and 10. 1 is mono. 2 is di. Tri. Tetra. If you have trouble remembering tetra, think back to Tetris, if you've ever played. Every shape in Tetris has 4 blocks. Tetra. 5 is penta. 6 hexa. Hepta. Octa. Non. Deca. So if it's covalent, you just have to describe each of the components using these terms, with a couple exceptions. If the first term has only 1, you don't say mono. So classic example of a covalent compound is CO2. Everyone knows this as carbon dioxide. If it's just 1 here, you don't say mono. We don't say monocarbon dioxide. We just say carbon. But you do need to include the mono if the second term has only 1. So another good example of a covalent compound is CO, carbon monoxide. You probably have a detector in your house. So again, we don't say monocarbon monoxide, but we also don't just say carbon oxide. You have to say carbon monoxide. Another quick exception here. Anytime you deal with oxygen, you're going to end up with something like, let's say we have 8 oxygens. You're going to end up with actually, 8's kind of a tough example. Let's start with 4. You'll see that a lot. You would have tetraoxide. Tetraoxide. It's a little difficult to roll off the tongue. So when you have the AO, you just cut the A out, and we just call this tetroxide. Okay? So that is naming covalent. So if it's covalent, use these Greek prefixes. If it's ionic, a little more difficult. There's one question you need to ask yourself at this point. So, look at the metal. Which we already said were all of these in red. Look at the metal, or look at the cation, which is the first part. Can this metal have multiple charges? That's a question you have to ask yourself. So some of these metals can have multiple charges, others can't. These metals here in group 1A all have a charge of +1 always. These have a charge of +2 always. These are your transition metals that can have multiple charges, but there are a couple exceptions in here. Starting at aluminum, we do 3-2-1 rule. Aluminum is always 3+, zinc is always 2+, silver is always 1+. So if you have any of those 3, or these, or that, or one other exception is ammonium. So if you look here, you can see ammonium is the only polyatomic ion that's actually positive. So if you have these, then the answer to this question would be no. Any other metal, the answer to this question is yes. So I'm going to start with the no. So let me write, if the cation can only have one charge, examples are metals in 1A and 2A. Doesn't include hydrogen. Remember, hydrogen's a nonmetal. Okay. Also, Al, Zn, Ag, or ammonium, NH4+. So any of these, we don't need to use Roman numerals because we don't need to specify what the charge is. It's set. For example, sodium, Na, is always Na+. Magnesium is always Mg2+. Aluminum is always aluminum 3+. So we don't need to use any Roman numerals. So all you do for this is state the name of the metal. Step 2, state the nonmetal, changing the N to "ide". So that's why classic salt is called sodium chloride. I'm going to say here, or if it's not an anion in the sense that it's like a single element, so if you don't have this, you're probably going to have some kind of polyatomic. So I'm going to say, or just state the name of the polyatomic ion. So I'm just going to say Pi. So basically you're going to state the name of the metal, state the non-metal, change the N to "ide," or state the polyatomic ion. Let's just do a couple quick examples. So if I have Al2O3, first question I always ask, is this ionic or covalent? Well, metal, non-metal, ionic. Next question, I look at the metal. Do we know the charge on aluminum? Yes, we do. It's always 3+, so I don't need Roman numerals. So to name this, I just say aluminum oxide. Another example, Mgi2. First question we ask ourselves, ionic or covalent? Metal, non-metal, ionic. Next question, do we know what magnesium is always? Yes, we do. Magnesium is always 2+. So I don't need Roman numerals, I just say magnesium iodide. Simple. Last example, NH4,2S. Little trickier. This is ammonium. This is sulfide. In this case, we're not looking at a metal, but we're looking at a polyatomic cation. Does this term always have a set charge? Yes, it does. Ammonium is always +1. Oops. Okay, we're good now. Losing battery. So, since ammonium is always +1, I don't need Roman numerals. I'm just going to call this ammonium sulfide. Just like that. Okay, now we've gone through the flow chart a little bit. So, if the metal is one of those transition metals that can have multiple charges, there's one extra step we have to take. So, if the metal can have multiple charges, we need to use Roman numerals. Okay, just a quick review if you don't know your Roman numerals. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The lines on the top and bottom are optional. Sometimes you'll just, in fact, when I write it quickly, I don't do the top and bottom lines. I just do the lines like that. But anyway, these are your Roman numerals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Make sure you memorize those. The most common ones to know are 1 through 6. You're not really going to deal with anything higher than 6 too often, but it's still good to know. And what the whole point of the Roman numerals is this. The Roman numerals indicate the charge of the metal. And that's what you have to demonstrate, or you have to signify this. So let's run through a couple examples of what I mean by this. Let's say you have COS. Okay? So again, first question we always ask ourselves, ionic or covalent? Metal, non-metal, ionic. Second question, look at the metal, cobalt. Do we know what the charge on cobalt is always? Where did my periodic table go? Cobalt is here. We do not know what the charge on cobalt is. Therefore, we need to use Roman numerals. So, what I have to do with Roman numerals is find the charge on the cobalt, and I have to report that in my formula. So how do I find the charge on this cobalt? I just said we don't know the charge on cobalt. Well, you use the non-metal part like a puzzle. So I know that sulfur forms an ion of S2-, always. And again, you find that out by looking at your periodic table. Here's sulfur. It has 6 valence electrons. It wants to gain 2 more. So it has a charge of 2 minus. So if there's one sulfur ion, that contributes -2 to the formula. Now remember, by being in an ionic formula, it is balanced. You can't have an ionic formula with a charge. This is neutral. But I'm saying the sulfur contributes -2 to the formula. So therefore, in order to balance it out, the cobalt must contribute just the opposite, +2. So the sulfur is -2, the cobalt must be +2 to balance it out. So we're going to call this cobalt Roman numeral 2 sulfide. So remember, the Roman numeral is the charge on the cobalt. Very common mistake I see, and it's important that you don't fall into this pattern. People mistakenly think that the number here is like the number of cobalt. So they'll say, oh, well, I have a cobalt, but I have one of them. So I'm going to write cobalt 1 sulfide. That's incorrect. The charge is this number here. And just to quickly demonstrate why we actually have to do this, let's run through a couple quick examples here. That works. So FeO, Fe2O3. These are two common formulas you're going to see. Now, if we didn't do this Roman numeral step, I would just call this iron oxide, I would call this iron oxide, but I can't do that because a formula or a name has to have a specific thing it refers to. So we need to be specific. So let's talk through what these charges are going to be. Let me go ahead and shift this one down a little bit for now. Alright. So, I need to find the charge on my iron, which I don't know, but I can use the oxygen almost like a puzzle. So, oxygen has a charge of 2 minus. So therefore, in order to balance this out, the iron must have a charge of 2 plus, because it's 1 to 1. So when I name this, I'm going to call it iron, Roman numeral 2, oxide. Down here, we're going to do something similar. But now instead of 1 oxygen, I have 3. So I'm not going to write -2. I'm going to say the total negative charge of this is -2 times 3. So it's -6. So therefore, the total positive charge that must cancel that out is going to be +6. But I'm not going to call this iron 6 oxide, because I need to recognize that the 6 positive charge is distributed among my 2 irons. So I have 2 iron atoms that together are +6. So therefore, each iron is +3. So again, 2 of these make +6. So each one must have a charge of +3. So I'm going to call this iron 3 oxide. Okay, so that's why we can't just call it iron oxide and iron oxide. You have to give it these specific names. Okay, so what I want to do next is run through some quick examples, and will involve covalent or ionic compounds. So let me make a list here. So let me grab my copy. All right. All right. So if you want to actually, you can pause, try to solve these, and then check. I'll give you a second for that. Okay, so let's work through these. First step we always say is ionic or covalent. Well, in this case, I see a polyatomic ion here and a polyatomic ion there, so this is definitely ionic. Next question I ask myself, I look at the metal or the cation. Do I know what the charge on this is always? Yes, I do. Ammonium is always +1. So I don't need any Roman numerals. I'm just going to simply name this as it's written, ammonium nitrate. Okay? Next one here. First question I ask, is this ionic or covalent? Sulfur and fluorine. We look at our periodic table. Sulfur, fluorine, two nonmetals, covalent. So I name this using Greek prefixes. I have one here. I don't say mono. I don't say monosulfur. I just say sulfur. 6 F's is hexafluorine, spelled F-L-U-O-R-I, and it's fluoride because you always add the I. So sulfur hexafluoride. Next example, BaI2. First step, is this ionic or covalent? Barium is a metal. Iodine is a nonmetal. This is going to be ionic. So next question I ask myself, do I know what the charge of the metal is? Yes, I do. Barium is always 2+, so we don't need any Roman numerals. I simply name this barium iodide. Next example here, cesium and oxygen. First question, is this ionic or covalent? Cesium is a metal. Down here. Oxygen is a nonmetal. Metal plus nonmetal, ionic. Next question, do I know what the charge on the metal is? Yes, I do. Cesium is down here in group 1A, so I know the charge is +1. So all I have to write is cesium oxide. Next problem, CO4. First question, is this ionic or covalent? Nonmetal, nonmetal. Two nonmetals, covalent. Carbon tetroxide. Remember, you don't say tetraoxide. You cut that A out and you say tetroxide. So I'm going to write that quickly. Carbon tetroxide. Just like that. Final example. Is this ionic or covalent? Well, nickel is a metal. Sulfur is a nonmetal. Metal plus nonmetal, ionic. Next question. Do I know what charge sulfur is? Do I know what charge nickel is? No, I do not. Here's nickel. It's in our transition metals. So I will have to use Roman numerals. Now, I have to determine the charge on that nickel in order to name this. So I don't know what nickel is, but I do know what sulfur is. Sulfur always forms a 2- charge. So therefore, the combined nickel must form a 2+ charge in order to balance this out. But since I have two nickels that together create a +2, each nickel must be a +1. So I'm going to call this one nickel 1 sulfide. Just like that. Okay, so this is examples of all the compounds that you're going to name. Make sure you check out the practice sheets we've done. If you're a chemistry student, there's plenty of examples on my Edline. Physical science students, I gave you plenty of copies in class, so run through these problems.